I had to put that. I just thought that was awesome, so it went on the slide. Okay, maybe my recording won't fail. I don't know. I recorded my exam review for concrete, and then it just sort of stopped. I don't know what happened. Okay, so exams are back. You all have that, and the exam grades are posted. So the only thing that we're waiting on right now in terms of grades is homework number 3, but that one was kind of big, and the exam's already over, so it's not like there's a super... Is it not? Did I do it again? It's more. Is it a Wednesday? I'm sorry. See, now I don't have my keyboard hooked up, so now I got to do this thing. Okay, and I know that some of it fed through. See, I go in and I just change the date, but then it says Wednesday. Maybe I should just remove the day so that, you know, I'm not causing too many errors. But it is due on March 6th, so that is true. Okay, so you all have a homework assignment, homework number 4, bolted connections. That's been uploaded today. It's due on March the 6th. After today, you should be able to handle most of it. The only thing that's going to be a little new is the combined loading problem. But the combined loading problem, if we don't get to it today, we're definitely going to get to it Wednesday. But there's no reason that you can't address number 1 and probably not number 2. There's 3 problems, and so number 1 and number 2 you should definitely be able to address by the end of business today. So yeah. Everybody good? What? Oh, thank you. I didn't know what you were talking about. Okay, thank you. That's awesome. All right, I do have one other announcement. Wednesday, like 2 days from now, in concrete design, we are having our first celebration in there. So I'm going to ask everybody a favor. We're going to go till 10:55, so hold off on coming in. So if you do me a favor there. So just hold off on coming in until the exam's over. I'm actually not going to be there for the first bit of it. I have an appointment on the other side of campus. So like I may come in like at 10:50, but I'll let everybody know when they can come in. All right? All right. Okay. So thank you. All right. So let's talk about, let's go back to bolted connections, and let's get back into the swing of things. Is this thing still recording? Yes, it is. I was like, why is it only recording for 2 minutes? I was like, oh, yeah, because I didn't record any of the exam solution. Okay. All right, so let me go back a few slides because I want to make sure that everybody's clear on this. Okay. So the last thing that we talked about was the difference between a bearing type connection and a slip critical connection. Now, a bearing type connection is subjected to the requirements of bolt shear capacity, or it must meet the requirements of bolt shear and bolt bearing. So if you have load on it, those are the 2 limit states that you need to withstand. And so that's ultimately, that ultimately guides how you design. So we determine the design load, we determine the shear capacity of a single bolt, we divide to obtain the number of bolts, and then we just lay it out according to spacing and edge distance requirements, and then check bolt bearing. Now, let's be absolutely clear. I'm not going to make you check gross section yielding, net section fracture, block shear rupture, any of that. Although theoretically, whenever you're designing connection and tension, there's all those other limit states that you need to check. We did this problem together, and this problem, I think we got, what was it, like 18? What was it? How many bolts? Was it 18 bolts? 15 bolts. Okay, so we got 15 bolts on this connection. We laid it out in a 5x3 pattern. We used 2-inch spacing along the plate and 1-inch edge distance spacing. Yeah, it was 2 and 1. And we didn't do the bolt bearing check, but you all have enough ammunition to do that on your own. And we talked about additional issues, and then we got into slip critical land. So slip critical land is when we're using enough pre-tension on the bolts that we can actually count on the friction that's developed between the 2 fang surfaces on the strength of the connection. There are specific locations where we do that, where we have vibratory loads, where we have fatigue considerations, where we it's not that uncommon to detail connections in that fashion in earthquake zones. So all bridges use slip critical connections. So it's a very fundamental type of bolted connection. Slip critical connections have to meet the requirements of bolt shear, bolt bearing, and this new slip resistance. And we went through all these different ways in which you can achieve a slip critical connection. I'm not going to go through all of them again because we've done it before. What I do want to do is very quickly review this. So this is the fundamental base equation to determine the capacity of a bolt according to slip resistance. And so ultimately, it's just the coefficient of static friction times a normal force. It's the fundamental static friction force equation that you learned from basic physics or statics or whatever class you saw it first in. So we take a coefficient of static frictions, or what is referred to in the manual as a mean slip coefficient. That's your mu value. You take mu and you multiply it by T sub B. T sub B is essentially your normal force. That's how much tension you're developing inside your bolt, and so that's the normal force that you get. So mu times T sub B, that's the physics side of it. The D sub U, the H sub F, and all that, those are all the adjustments for reality and things like that. So mu, that's a lookup, 0.3 for Class A, 0.5 for Class B. And the difference between the two is basically a reflection of the surface characteristics. If you have blast clean steel, you develop better friction between the two plates, whereas normal everyday steel, a mu of 0.3 is expected. D sub U is that multiplier that reflects the actual pretension that you get versus what you specify. On average, you get more pretension in the field than what you actually specify, so it sort of should give you some comfort that those prescribed methods like turn of the nut and using a DTI or twist-off control bolts, all those things are very valid means to generate specified pretension, because you usually get that and then some, because that value is over 1. The engineer of record can specify a different value if they want, but that almost always never happens. T sub B, that's the actual minimum pretension force that you get. It's roughly equal to about 70% of the minimum tensile strength of the bolt. That's just rounded off to the nearest kip. The filler plate factor, that's if you're splicing beam A to beam B and you have multiple filler plates to try and even out that thickness. But we never really have to worry about that for the purposes of what we're doing in this course. And N sub S, that's just the number of slip planes. So if you had multiple slip planes, you could double your capacity, but it's kind of like, it's basically the same thing as the number of shear planes. So it's just the number of fang surfaces, or the number of locations that you can develop that slip capacity. The big thing that I want everybody to be clear about is that all of these parameters, just like bolt shear capacity, all of these parameters are in here. So if you turn to table 7-1, that's this table that lists the capacity of each bolt, right? Because everybody brought their AISC 15th edition steel construction manual, that turquoise book that I see on everybody's desk. Yeah. Oh, there we go. There we go. I didn't know you were looking for it. Never mind. I apologize. Everybody has their AISC 15th edition steel construction manual, right? So if you turn to table 7.1, 7.1 lists the shear capacity, average shear strength of a bolt. Just turn the page, and you'll see table 7.3, and we have here slip critical capacity. Now, if you look, the way that this is organized, so the page on the left is group A bolts, the page on the right is group B bolts. Now, you can turn the page and there's a group C bolt, but we're never going to use group C in this course, so you don't have to worry about that. Now, one of the things that you notice for both of these tables is what? Like, what's going on with the table? It's for group A bolts, but what is also held constant for both of these tables? We know the group. What else? The friction factor, the Class A fang surface. So can we use this table for a Class B fang surface? The answer is yes. We have to multiply the capacity, though, by what? Everybody see that on the bottom? 1.67. Why are we multiplying by 1.67? Well, the reason why is right here. If it's a Class B fang surface, it's 0.5. So what's 0.5 divided by 0.3? It's 5/3. It's 1.67. So if you have a Class B fang surface, you can use this table. You just have to multiply by 1.67 to reflect the higher frictional capacity. So that's it. It's pretty straightforward. Some notation that you might see on the left that's a little new. So first off, unless otherwise noted, we're always going to be using standard bolt holes in this class, but there's a couple other options. So if you have a standard hole, or let's say an oversized hole, or a long slotted hole, or a short slotted hole, and then whether or not the slot is parallel to the direction of load or transverse to the direction of load. Basically, if you have larger hole diameters means you develop less friction. So less friction means weaker bolt. And so you can kind of see that pattern if you start looking at the bolts, the bolt holes. Basically, as the bolt holes get bigger, the bolt capacities get smaller. But you really don't have to do much in terms of capacity. It's very similar to bolt shear. All you have to do is say, here's my bolt diameter. I'm looking at a Group A bolt. It's 3/4 inches in diameter. It's single shear. Bam, there's my capacity. So it's a pretty straightforward lookup. There's really not a whole lot to it. And so I want to exercise that using the following example. So I want to design this connection, and I'm not going to go full out into this design example because this example is going to be really short. Now I'm going to be absolutely clear. It would probably be a lot longer on your homework assignment because you have to go through all of this. You have to look at your bolt layout requirements. You have to look at your edge distance requirements, spacing. I'm not going to get into all that. I really just want to make sure with this example that you're comfortable with looking up the value here. That's really all this example is about. So we have a Group B in 3/4 inch diameter bolt. We have A572 grade 50, although that's really not going to matter for the purposes of what we're talking about in here. And what we need to do is determine how many bolts we're going to use. And so I'll show you something about this example as we get into it, and I think you'll see what I mean. So let me end this. Okay. So first off, if we're in design land, what do you think is the first step that we need to do? We need to factor the load. So let's determine a factored load. So we have a dead load of 65 kips and a live load of, is it 110? So 1.2 dead plus 1.6 live. All right, hold on. $262 kips. Do I have a second on that? Somebody said no? Okay, yeah. Well, it's possible. Remember that I can't stress this enough. On an exam, like second yourself. Like do the math and do it again. Guarantee you. Averages will go up. Guaranteed. Oh. All right. Now, in terms of design, here's sort of how this works. Okay, so the first thing I'm going to do is look up bolt shear capacity. Because just because this is a just because this is a slip critical connection, it does not mean that the connection we don't have to worry about bolt shear. We most certainly do. See, if the slip fails, the connection automatically becomes a bolt bearing connection. Because see, if that friction fails, what happens? Those bolts engage, right? And so we still have to meet the requirements of bolt shear and bolt bearing. So let's talk about these bolts, okay? So what's the deal with the group? Is it Group A, Group B? What's the deal? So Group B, and then is it excluded or included? If I didn't tell you whether or not it was included or excluded, what would you do? Assume what? Assume that they're included, because the threads included inside the shear plane are going to mean a weaker connection. So always assume the worst case scenario. What is the bolt diameter? And what about the shear? Are we in a single shear scenario or a double shear scenario? Single shear. Single shear scenario. So help me out. If we are talking about the shear capacity of a bolt, so what I'll do to indicate that is I'll say phi Rn, but I'll say phi Rn V. I'll put a little V on there to indicate shear. What would the shear capacity of a bolt be? Say it again. 22.5 kip per bolt. Okay? Is everybody else able to find that? Well, somebody, where did you find that? Somebody tell me. (7-22). What? So we're not on slip critical yet, okay? We're not on slip critical. All right? Everybody okay with this? Okay. The only thing that's different moving forward is now we have another value to look up. Now we're going to look at bolt slip capacity. Okay, and so let's start listing the parameters associated with bolt slip that are going to be important. And so we can turn to table 7-3 and let's start writing down the things that matter. So first off, what's the deal with the groups? Are we in group A or group B? B. So we have group B. What about the threads being included? Does that matter? It doesn't matter, okay, because we're not talking about shear, we're talking about slip. So whether the threads are going to be sheared through or not doesn't matter if we're not talking about shear. Now, we do still have a bolt diameter of 3/4 of an inch, okay. We're dealing with a standard hole. I'll go ahead and put that, although we pretty much are always going to be dealing with a standard hole. What about our fang surface? Do we know what fang surface we have for this problem? We don't. So if you don't know, what are you going to do? What's the most conservative assumption? Assume what? Say, well, no, that's the group, the bolt group. Yes, so we're always going to assume, so maybe what I'll do is put that in red and I'll say, assume class A. It'd be like if I didn't tell you whether or not the threads were included, always assume, same deal here. So if I have a bolt that is 3/4 inches in diameter, it's group B. Oh, hold on, there's one more thing. Is this single slip or double slip? So what would the phi, and what I'll do is I'll write this. I'll say phi Rn, we'll say SC. What is that going to be? 11.9. So we'll say that's table 7-3, page 7-25. Now, is everybody else able to find that? What?
Did it specify what the retention was? Why did we use under the...
I don't. Oh, that's a good question. That value is associated with that bolt diameter.
Oh.
See, that value is associated with that. So the 35 kips, that 35 kips that you see right there, that's T sub B for that bolt. So if you want, you could take 35 kips times 0.3, as your mu value, times 1.13, times all this, and compute these values. But I'm lazy. I'm just going to use a table. So, is everybody okay with this? So which is weaker, the shear capacity or the slip capacity? So if I load this bolt, do you think it's going to fail and slip first or fail and shear first? Slip. Okay. Now this is, we don't like to use the term always and nevers, but more often than not, this tends to happen. It's not always the case, but more often than not, it tends to happen. And a lot of times with most regular scenarios, the slip capacity is about half the shear capacity. So if you're designing a connection and you suddenly decide it's going to be slip critical, you're probably going to do something like double the amount of bolts. And that's sort of a rule of thumb there. Now, if you want to determine how many bolts you would need, it's pretty straightforward. We're going to design based off of the slip capacity. So PU was what? Was it 262? So help me out. How many bolts are we going to need, theoretically? What's the theoretical value going to be? I have 262 kips on the connection. Each bolt can hold 11.9s. How many bolts am I going to need? 22? Well, what's the number come out to be? 22.02. Say it again. 22.02. So, yeah, I mean, you could, I'll be honest, in a scenario like this, I'm not going to lie that I might be tempted to use 22 bolts because it's so close. But in all honesty, if we're being conservative with our designs, we probably would need to round that up. And I probably wouldn't round it up to 23 bolts because arranging 23 bolts in a nice, neat, organized pattern would be kind of difficult. So I'd probably say something like use 24. Now, the remaining steps, because I'm not going to do it because we've already done this before and it's literally just the same thing over and over again. Lay out the connection. Getting ahead of myself. Check bolt bearing. And if necessary, check tension member. Limit states. Let me ask you a question. Yes. Just like you don't really need it for shear because everything's tabulated. So, but I do want you to understand it. So, yes. Yeah, I would. Short answer, yeah. But also on the homework assignment, I think I go a little bit step further and I'll say things like assuming 3 lines of bolts. So if there's going to be 3 lines, it's going to be like 3, 6, 9, 12, 15, 18, blah, 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 you know, so I even give you a little bit more guidance there. Yep. What's that? You could, yeah, you could. So exactly. Now, does everybody know what I mean when I say lay out the connection or check bolt bearing? Because we've done that in previous examples. This is the time. Now, we still got a few minutes. I'm going to introduce our next topic before we leave. So. I know it was going. Any questions? All right. That means you're going to get 100 on the homework, right? All right. All right. I need your attention for the next 4 minutes. All right. So, everybody pay attention. Shh. Okay, all right. So, up until now, what we've been doing is we've been restricting our discussion to a situation where all we're investigating is bolts in shear. Okay? Here's what I mean by that. okay? Here's a bolt, plate A, plate B. Plates connecting them, and we're loading it like this, okay? Whether or not the bolt's going to fail and bolt shear or bolt bearing or whatever, we're still talking about a connection that is loaded primarily in shear. What if the connection looks like this, okay? Where we have, let's say, some load and we're trying to design these bolts. These bolts would not be loaded in shear, they would be loaded in tension. And so the idea of slip or bolt shear, bolt bearing, all that goes out the window because we're talking about a completely different set of mechanics. Now, fortunately, the design of a series of bolts like this is really no more different or more difficult. In fact, it's in some cases a little easier than the design of bolts in shear. It's the same idea. Determine the capacity of a bolt, divide to get the total number of bolts. Now, the capacity is a little different because we're talking about tensile capacities and not shear capacities, but theoretically it's a lot easier. We don't really care how many threads are included in the shear plane because we're not shearing it. We're yanking on it, so that doesn't matter. It also doesn't matter how many shear planes there are. There could be 86 shear planes, and we're still just yanking on it. In fact, this equation is the exact same equation for threaded rod design. It's no different. If you go to table 7-1, that's the shear capacity. Literally, the table next to it gives you the tensile capacity. Really easy to determine, okay? What I want to do next time is I want to talk about that, okay? What I want to ask is, what happens if you have a connection loaded like this, okay? Because this type of connection, which would be really common in like a bracing connection or a truss or something like that, sees a series of bolts that are loaded in both shear and tension. In other words, if I take this load and split it up into its X and Y components, the X component is yanking on these bolts this way in tension. The Y component is wanting to shear these bolts. So how do you determine the capacity of a bolt that is seeing both tension and shear? That's a little tricky, okay? Because, what? Well, that's a fair way of looking at it, and we do kind of do that. But what we also have to address is the interaction between the two forces. So here's what I mean by that. If I have a bolt loaded to like 99% of its shear capacity, like I put a feather on it, it's going to snap. I can't expect that at the same time it's going to develop 100% of its tensile capacity. It's so loaded to bear and shear that it probably just can't handle that much in tension, and vice versa, okay? If I got that bolt and I'm stretching it until it's about to snap, I probably can't shear it very much because it's probably going to fail as well, okay? If you have a combination of shear and tension on the bolt, you have to basically assess three checks. You have to assess the capacity of the bolt in shear, the capacity of the bolt in tension, and how those two forces interact with one another. And that's what we're talking about with interaction. For those of you who've already had concrete design, you've already seen interaction before. Remember at the very end of class when we had the PM curves? Remember that? You had an element that was seeing both axial load and bending. And so you couldn't do 100% of the axial load and 100% of the bending. You had to use those beam charts to figure out what our capacity was going to be, or those beam column charts, those PM curves. We're going to have something a little bit more simple and a little bit more straightforward here, but I really wanted to introduce this concept because this is really important for the purposes of what we're talking about. We're going to talk about the math in very significant detail next time. That's all I got.